Hi guys, this is Circles, and the topic for this video is improper integrals. So, recall from your lecture that we will cover two improper integrals or two types of improper integrals, namely the one with infinite intervals. Okay, we will call that the type 1 improper integral, and then the other one is with infinite discontinuity. So we will call that type 2. So let us now proceed with our examples here. So for our first example, so we want to integrate integral from 3 to plus infinity of 1 over quantity x minus 2 raised to 3 halves dx. So first, observe that the integrand here, we have a discontinuity at x equals 2. However, the interval of integration here is from 3 to plus infinity. Okay, so this means that this integral here is actually continuous from 3 to plus infinity, and therefore this is a type 1 improper integrals. And in order to solve this improper integral, what we do is we take the limit as t goes to infinity of the integral from 3 to t. Here you have dx divided by x minus 2 raised to 3 halves. So this guy here, integral from 3 to t of dx over x minus 2 raised to 3 halves, this is just ordinary definite integral. So when we evaluate this integral here, what we will obtain is an expression in terms of t. And after we get that expression, that's the time we pass to the limit as t approaches infinity. So let us work on the definite integral inside. So in here you can write limit as t approaches infinity of the integral from 3 to t. This guy here, you can write it as x minus 2 raised to negative 3 halves dx. And with simple substitution, we let your u be equal to x minus 2, du will be dx. So this guy here becomes u raised to negative 3 halves. And then if we do the integration, we will end up with u raised to negative 1 half over negative 1 half. So we will skip that u substitution, and therefore we'll just write limit as t approaches plus infinity of x minus 2 raised to negative 1 half divided by negative 1 half, and then we evaluate this from 3 up to t. So we now have limit as t approaches infinity, and then in here, if we substitute now x equals t, we will get negative 2 times t minus 2 raised to negative 1 half. Okay? And then minus, you have negative, so at x equals 3, we will have minus 2 times 3 minus 2 raised to negative 1 half. And then we have the closed bracket here. So this guy here we can simplify immediately. So 3 minus 2, that's just 1, and we have square root on the denominator. So that's just square root of 1, which is 1. So this guy here, it's just plus 2. Okay? So we will get limit as t approaches infinity. While for this guy here, we can write this as negative 2 over t minus 2 raised to positive 1 half. And then let's add that 2 coming from this. And now, observe, as t goes to plus infinity, t minus 2 will go to plus infinity. You take the square root of that, it will still go to plus infinity. And it is on the denominator, which means this guy here will go to 0. And therefore, this improper integral here is simply equal to 2. So this is the answer to this improper integral. So next, we want to integrate from 0 to plus infinity of x squared over square root of 1 plus x cubed dx. Now, observe we have a denominator square root of 1 plus x cubed. And the 1 inside the square root, 1 plus x cubed, will be greater than or equal to 0 when x is greater than or equal to negative 1. Okay? In fact, the denominator will be 0 at x equals negative 1. So combining all those facts, we see that this expression here, x squared over square root of 1 plus x cubed, it is continuous on the interval 0 to plus infinity, which means this is a type 1 improper integral. And therefore, we write this as the limit as t approaches infinity of the integral from 0 to t of x squared over square root of 1 plus x cubed dx. Now, let us look at this definite integral. In fact, let us work on the indefinite integral x squared divided by square root of 1 plus x cubed dx. So in here, we do some substitution. We let u be equal to square root of 1 plus x cubed and du. This is equal to 3x squared divided by 2 square root of 1 plus x cubed dx. Or simply, we have 2/3 du equals x squared divided by square root of 1 plus x cubed dx. So what does this mean? This integrand here will be replaced by 2/3 du. So we have the integral of 2/3 du, and this guy here, it's just 2/3 u plus the arbitrary constant c. And if we bring back the variable x, this is just 2/3 square root of 1 plus x squared or x cubed. And then you have the plus c. So going back to this definite integral, we now write this as the limit as t approaches plus infinity. We have this 2/3 square root of 1 plus x cubed, and we evaluate this from 0 to t. And therefore, we will get limit as t approaches plus infinity. Let me factor the 2/3. At x equals t, we just have square root of 1 plus t cubed. And then minus. At x equals 0, this is just the square root of 1, which is simply 1. Now, as t approaches plus infinity, square root of 1 plus t cubed will also approach plus infinity. We subtract 1, it's still plus infinity. You multiply by 2/3, it's still plus infinity. So we will get plus infinity, and therefore this improper integral is said to be divergent. Okay? Next problem, integral from negative infinity to plus infinity of x e to the minus x squared dx. Now observe, the exponential functions, they are continuous from negative infinity to plus infinity. The polynomials are also continuous on the interval negative infinity to positive infinity. And if you multiply them, they are still, or it is still continuous from negative infinity to plus infinity. Hence, this integrand here is continuous from negative infinity to plus infinity. But the lower limit of integration is negative infinity. The upper limit of integration is plus infinity. So what we're going to do is to divide this into two integrals. Okay? We choose a number in between negative infinity and plus infinity. And here we choose 0. So we rewrite this as integral from negative infinity to 0 of x e to the minus x squared dx plus the integral from 0 to plus infinity of x e to the minus x squared dx. So these two guys here are improper integrals, type 1. Both of them are type 1. Okay? So we apply our methods in that type 1. Let us rewrite this first here as the limit as t approaches negative infinity of the integral from t to 0 x e to the minus x squared dx plus limit. Here, since we used the parameter t already, let's use another parameter here, a different parameter, say s. This time s goes to plus infinity, and we have the integral from 0 to s, x e to the minus x squared dx. So in here, let us work first finding the antiderivative of x e to the minus x squared. So let me put the work on this part. So we want to integrate x e to the minus x squared dx. So we easily see, we use substitution, u equals, say, e to the minus x squared. And then du will be equal to 2x or minus 2x e to the minus x squared dx. So that this integral here, okay, can now be written as negative 1/2 integral of du, and this is minus 1/2 u plus c, and therefore this is simply minus 1/2 e to the minus x squared plus c. So we now have an antiderivative. Let's put that antiderivative in here. So we will have the limit as t approaches negative infinity of negative 1/2 e to the minus x squared evaluated from t to 0. So this is the first part. Plus, you want the limit as s goes to plus infinity. Again, negative 1/2 e to the minus x squared evaluated from 0 to s. Okay? And let us do the evaluation. This is now limit as t approaches negative infinity. Let me factor that minus 1/2. And at 0, this is just e to the 0, which is 1. And then minus at t, e to the minus t squared. Okay? And then for the other guy, we will have plus the limit as s approaches infinity. Okay? Again, we factor out negative 1/2. So we will obtain e evaluated at s here, e to the minus s squared minus e to the 0. Okay? And now, notice, we recall exponential function, the graph of exponential function here. The graph of exponential function is something like this. So, as the, say here, x, and then y here, as x goes to negative infinity, this guy here will go down and down and down to 0. Okay? So what does that mean? As t goes to negative infinity, we have t squared here. So whatever your t is, if you square it, it becomes positive. So we will get e to the minus infinity, because again, you square your t, it becomes positive infinity. As t approaches negative infinity, t squared will approach positive infinity. And we have a negative here, so we have e to the minus infinity, and that is equal to 0. This will go down and down and down to 0. Okay? So that's for the first part. Well, we have minus 1/2 e to the 0. That's just minus 1/2. And as I have said, this will go to 0. And then plus, we have here minus 1/2. Okay? And then e raised to negative s squared. S going to plus infinity, so s squared is still plus infinity. Okay? And then e to the minus infinity, again, that's just 0. And then here you have minus 1/2 times minus e to the 0. And that will give us a plus 1/2. And this is equal to 0. Okay? So this means this improper integral is simply equal to 0. Okay? So there is a value, and therefore we say that this is convergent. By the way, in the first example, okay, in the first example, we also got a value here, so it is convergent. Okay, so let me just write that one here. Okay. Don't be confused. The graph that you see here, this is the graph of your y equals e to the x. Well, roughly, this is your y equals e to the x. Okay? So this graph here, it's not this function that you see here, or this expression that you see here, x e to the minus x squared. So this guy here, it's your y equals e to the x. Next example, we want to integrate negative infinity to 0 of x e to the 2x dx. So same explanation as before, x e to the 2x, this is continuous on the interval negative infinity to 0, which means we can write this now as the limit as t approaches negative infinity of the integral from t to 0 x e to the 2x dx. And then let's work on this integral here. Particularly, let's find the antiderivative of x e to the 2x dx. You can use IBP. Remember Liate? So this is algebraic, this is exponential, so we can let u be equal to x, dv equals e to the 2x dx. du, this is just 1, and then v, this is e to the 2x over 2. Okay? Sorry, the du here must be dx. Therefore, we have uv, so x e to the 2x divided by 2 minus the integral of v du. So e to the 2x over 2 dx, and therefore this is equal to e to the 2x or x e to the 2x over 2 minus e to the 2x divided by 4, and then plus the arbitrary constant c. Okay? And then for this, we have the limit as t approaches negative infinity of the integral. We have it here, x e to the 2x divided by 2 minus e to the 2x divided by 4, and then we evaluate this from t to 0. And after evaluating, at 0, this guy here will be 0 times e to the 0. Well, this is already 0. Okay? So, this guy here is 0. Then minus. At 0, you have e to the 0, so that's minus 1/4. And then at t, so we have minus t e to the 2t. Okay, e to the 2t divided by 2 minus e to the 2t divided by 4. Okay? So now, we look at the limit as t approaches negative infinity in here. Negative infinity in here. So approaches negative infinity. So if you look at this, as t approaches negative infinity, e to the 2t will go to 0. But you have a multiplier t here. So you will get what? Infinity times 0, and that is an indeterminate form. So I hope you still remember your indeterminate form. Okay? So let us write. First, this guy here, you have minus 1/4. And then for this guy, let's write minus limit t approaches negative infinity of t e to the 2t divided by 4. And then again for this guy, as t approaches negative infinity, e to the minus infinity will go to 0. So this guy here, it's just 0. Okay? And for this, let us rewrite this in another indeterminate form. So we have 1/4 minus limit as t approaches negative infinity. We'll rewrite this as t over 4 e to the minus 2t. And why is that? because as t goes to negative infinity, numerator goes to infinity, minus infinity to be more particular, and e to the minus 2t, this goes to e to the plus infinity. So denominator will also be infinity. So this is an indeterminate form of type infinity over infinity. So we apply L'Hopital's rule. Try to recall L'Hopital's rule. So we have minus 1/4 minus limit as t approaches negative infinity. For this guy here, we have what? 1. Just a moment. For this, we have denominator 2. So this guy here will have denominator 2. Okay? And also for this guy here, we have denominator 2. Anyway, let us continue. So L'Hopital's rule, we get the derivative of t, that's just 1. For the denominator, we also get the derivative. We get minus 4 e to the minus 2t. And notice, as t goes to negative infinity, denominator goes to plus infinity or minus infinity because of this negative. But whatever, this whole guy here, as t goes to negative infinity, will just go to 0. And therefore, we will have minus 1/4. So again, this guy here will go to 0. So we have a value, negative 1/4, and therefore, we have a convergent improper integral. Okay? Next example, integral from negative 1 to 0 of e to the 1 over x all over x cubed dx. So observe the integrand. We have a denominator x here. We have a denominator x cubed here. So this rational expression is actually discontinuous at x equals 0. Otherwise, this is continuous. Therefore, this expression here, or this improper integral here, is a type 2 integral. Now, we write this as the limit as t goes to 0 from the left. Okay? Take note, you have the interval from negative 1 to 0, so it will approach, or t should approach 0 from the left, of the integral from negative 1 to t, okay, of e to the 1 over x all over x cubed dx. Now, let's work on the definite integral here. Particularly, let's just work on the indefinite integral e to the 1 over x divided by x cubed dx. So we use substitution. U equals e to the 1 over x du. We will have here e to the 1 over x times the derivative of 1 over x. You have negative 1 over x squared. And then you have the dx. Okay? So, we have the e raised to 1 over x, we have the x squared, and we will be left with 1 over x in here. Okay? From this expression, we get 1 over x equals ln of u. Okay? We get 1 over x equals ln of u. So this guy here can now be written as negative integral of ln of u du. Okay? And therefore, if you remember the integral of this, you can write it immediately. If not, let's just integrate this again. So integration by parts. We say u1 equals what? Ln of u dv equals du, and then du1, this is 1 over u du, and then v, this is simply u. So we get minus uv or u1v, okay? That is equal to u ln of u minus the integral of v du1. So you just have du in here, and therefore you will get minus u ln of u plus c. But u is equal to e to the 1 over x. Okay? So let us write that in here. Okay? Let us write this in here. But with the substitution u equals e to the 1 over x, we bring back e raised to 1 over x. So we have the limit as t approaches 0 from the left of minus e to the 1 over x ln of e to the 1 over x. And then you have minus here. So it becomes plus here. So plus u, which is e to the 1 over x. Then we close this and evaluate from negative 1 up to t. Okay? And of course, ln of e to the 1 over x is just 1 over x. Okay? So let me rewrite that again. We will have the limit as t approaches 0 from the left of negative e to the 1 over x. Okay? And then plus e to the 1 over x evaluated from negative 1 to t. And this is equal to the limit as t approaches 0 from the left. At t, we will have minus e to the 1 over t divided by t plus e to the 1 over t. And then at negative 1 minus at negative 1, we will have minus e to the negative 1 over negative 1 plus e to the negative 1. So this guy here, it's just a number. We need to calculate this guy. But as t approaches 0 from the left, of course, your t will just go to 0. While in here, e to the 1 over 0 from the left. 1 over 0 from the left, that's negative infinity. And here, we will have what? E to the minus infinity, and that's equal to 0. Therefore, you will have here 0 over 0. So for this guy, it's an indeterminate form of type 0 over 0. This guy here, as t approaches 0 from the left, 1 over t will go to negative infinity, e to the negative infinity, that's equal to 0. So we'll just have to worry about this now. Okay? This is of type 0 over 0, so we can use E, or we can use Lopital's rule. So if we use L'Hopital's rule there, so L'Hopital's rule, we have the limit t approaches 0 from the left. And then we go, anyway, let me separate this solution. Let me separate the solution in here. So we want to get the limit as t goes to 0 from the left of minus e to the 1 over t divided by t. And we said that this is 0 over 0 type. Okay? So we want to apply L'Hopital's rule at this particular form. Okay, at this particular form, we will have limit t going to 0 from the left. We get the derivative of the numerator. We will get what? 1 over x squared e raised to 1 over t squared e raised to 1 over t, while the denominator, it's just 1. We get the derivative of this, you'll just get 1. And what you see here is actually limit as t approaches 0, and then e raised to 1 over t divided by t squared. And as you can see, instead of making this simpler, okay, it gets more complicated. So what I'm saying is we are not going to apply L'Hopital's rule in this particular form. So what we're going to do, okay, what we're going to do is to rewrite the expression in the following manner. So limit as t goes to negative 0 from the left, we will rewrite this as 1 over t all over e to the minus 1 over t. And we have a negative here. They're the same. They're the same. But this time, you have the form infinity over infinity. And you can still apply L'Hopital's rule. So by L'Hopital's rule, this is equal to the limit as t approaches 0 from the left. And then in the numerator, you will get the derivative of 1 over t. You'll get negative 1 over t squared. We have a negative here, so we will have 1 over t squared. And in the denominator, you get the derivative of this. We already had it here, but this time we will bring out a negative because of this. And then, by chain rule, we get the derivative of negative 1 over t. That becomes plus 1 over t squared. So essentially, what you will get here, it's 1 over t squared e to the minus 1 over t. Okay? E to the minus 1 over t. I think there's a negative outside here. Just try to check. Just try to check that one. But the point is, 1 over t squared and 1 over t squared in the denominator will be cancelled. 1 over t squared in the numerator and 1 over t squared in the denominator will be cancelled. So what we will get now is the limit as t approaches 0 from the left. And then we bring this up here, again in the numerator. So e to the 1 over t now. Oh, so even if we have the negative there, as t approaches 0 from the left, 1 over t will go to negative infinity, and e to the negative infinity, that's just 0. So this guy here is equal to 0. Okay? And therefore, what do we have? This will go to 0, this will go to 0, we'll have this guy here. So it's just negative 2 e to the minus 1. Negative because you have minus here and minus here, that's positive, and we have a negative outside here. So this is the final answer. And again, this improper integral here, it's convergent. Okay? Next, integral from e to plus infinity of dx over x ln x squared. Okay? So for this guy here, x denominator, so can't be 0. ln of x squared can't be 1. Okay? Because if that's the case, ln of 1 is 0, so we will have 0 in the denominator. So, in a sense, we cannot have x equals 0 and x equals 1. But our interval here, it's from e to plus infinity, which means what? This function, 1 over x ln of x squared, is continuous from e to plus infinity. So this is again a type 1 integral. So we have the limit as t approaches, say, plus infinity. Integral from e to t of dx over x ln of x squared. But recall properties of logarithm. This is simply what? Limit as t approaches plus infinity. Integral from e to t of dx over 2x ln of x. Correct? So if we look at the integral here, the definite integral here, it's a simple substitution. Okay? So again, we work on that integral. We have integral dx x ln of x. We can let u be equal to ln of x. Du equals 1 over x dx. So this guy here will become integral of 1 over u du. Okay? And therefore, this is just ln absolute value of u plus c. So in a sense, here, we will have limit as t approaches infinity. We have the 1/2 there. So 1/2. And then we have the ln absolute value of u. But u, it's ln of x. So ln of the absolute value of ln of x. Okay? We evaluate this from e to t. And therefore, we will have limit as t approaches plus infinity 1/2. At t, you have ln absolute value of ln of t minus 1/2 ln absolute value of ln of e. But ln of e, it's just 1. ln of 1 is 0. So this will just disappear. Now, as t goes to plus infinity, ln of t will go to plus infinity. ln of going to infinity will also be infinity. So this is simply plus infinity, and therefore, this improper integral here is divergent. Okay? Next example, integral from e to plus infinity of dx over x ln squared x. So, very similar to this, except that the squared now is on the ln function. Okay? So, same explanation as in before. This integrand here, this is continuous on the interval e to plus infinity. And therefore, this is again a type 1 improper integral. So, we write this. Limit as t goes to plus infinity. integral from e to t of dx over x ln squared x. So if we look at the integral again, particularly the indefinite integral or the corresponding indefinite integral, same as in before, okay? Same method as in the previous example, except that the denominator will be changed. So here, you have the integral dx over x ln squared x. Still let u be equal to ln of x du. This is equal to 1 over x dx. So, this guy here becomes the integral of 1 over u squared du. And this guy here, this is negative 1 over u plus c. And then you bring back that ln of x again. So in here, we will have the limit as t goes to plus infinity of negative 1 over ln of x evaluated from e to t, and this is equal to the limit as t approaches infinity of negative 1 over ln of t plus, because this is negative, so minus minus, so that's plus, 1 over ln of e. 1 over ln of e. And as t goes to plus infinity, 1 over ln of t will go to 0. Because ln of t will go to plus infinity. So this expression here, as t goes to plus infinity, this will become to 0. This will go to 0. And this guy here, it's 1 over ln of e, but ln of e, it's just 1. So this is the answer here. And therefore, the improper integral is convergent. Next, we want to integrate from negative 2 to plus 14 of dx over 4th root of x plus 2. So, observe that this integrand here, 1 over 4th root of x plus 2, is continuous on the interval negative 2 to plus infinity, excluding negative 2. We exclude negative 2 because when x equals negative 2, x plus 2 will be 0, and this is on the denominator. So this guy here, okay, is an improper integral of type 2. So here we now write limit as t approaches negative 2 from the right. Okay, this is on the lower limit, so we are approaching t. We are approaching negative 2 from the right of the integral t up to 14 dx over 4th root of x plus 2. So in here, we can easily get the integral. So let's work on the corresponding indefinite integral. So you have the integral of x plus 2 raised to negative 1/4 dx. Integrating this, we will have x plus 2 raised to negative 1/4 plus 1, that's 3/4, all over 3/4, plus the arbitrary constant c. Which means this guy here is now limit as t approaches negative 2 from the right. We now have the integral. We use this antiderivative here. And let us write this as 4/3 quantity x plus 2 raised to 3/4. And then we evaluate this from t up to 14. So evaluating, we will have limit as t approaches -2 from the right. We have here 4/3 quantity. At 14, you have 14 plus 2, that's 16, raised to 3/4. So 4th root of 16, that's 2, cube it, that's 8. And then here we have minus quantity t plus 2. So, what do we get? We have 4/3. And then, as I have said, 16 raised to 3/4, that's 8. Okay, 2 times 2, that's 4, times 2 times 2, that's 16. So 4th root is 2, cube it, that's 8. And then here, as t goes to -2 from the right, we'll just have -2 plus 2, that's equal to 0. So you can rewrite this as 32 over 3. So this is the final answer, and therefore we say that we have a convergent improper integral. Okay? Finally, my last example, we want to integrate from 0 to 9 of dx over cube root of x minus 1. So, the function y equals 1 over cube root of x minus 1, it is continuous except at x equals 1. Because at x equals 1, this will be 0 and we don't have any, we don't want that. Of course, if x is less than 1, we'll have negative number here, but we are getting the cube root, so we still have a value. So this guy here, it's continuous except at x equals 1. So what we're going to do is to divide this into two parts, and in particular, at the point of discontinuity, we have the we write integral from 0 to 1 dx over cube root of x minus 1 plus integral from 1 up to 9 of dx over cube root of x minus 1. And then these are now two improper integrals. So we write limit for this guy here, limit as t goes to 1 from the left, integral 0 to t dx over cube root x minus 1 plus, for this guy, we use another parameter. Let's just use s. So limit as s goes to, this time, 1 from the right, okay, of the integral from s up to 9 dx over cube root of x minus 1. So let us work on the corresponding indefinite integral. Okay, we have here, we want to integrate dx over cube root of x minus 1, and as in before the previous example, we rewrite this as x minus 1 raised to 1/3 dx. So if we integrate this, we will have x minus 1 raised to 2/3 divided by 2/3. And then we have the plus c. Which means, in here, we have limit as t approaches 1 from the left of. So we have here, we write this as 3/2 x minus 1 raised to 2/3 evaluated 0 up to t, okay, plus we have the limit as s goes to 1 from the right, of 3 halves. Quantity x minus 1 raised to 2/3, evaluated from s up to 9. So, at t, we just have 3 halves here, or limit, limit. T approaches 1 from the left. We have 3 halves times. At t, you have t minus 1 raised to 2/3. And then at 0, we have negative 1 squared, or negative 1 raised to 2/3. That's positive 1. Correct? You get the cube root of negative 1, that's negative 1. You square it, that's positive 1. So that's just positive 1. So minus 1. Okay? And then plus limit s goes to 1 from the right. You have the 3 halves quantity. At x equals 9, we have 9 minus 1. That's 8. You take the cube root, that's 2. And then you square it, that's 4. So you have 4 in here. Then minus quantity s minus 1 raised to 2/3. So, passing to the limits, here t goes to 1 from the left, this will disappear. This will go to 0. So we will only have 3 halves times negative 1. So minus 3 halves, then plus. As s goes to 1 from the right, this will go to 0. So we'll just have 4 in here. So 3 halves of 4, that's just 6. Okay? Or 12 halves. And therefore, simplifying this, we will have 9 halves. Okay? So this is our final answer, and we say that this improper integral here is convergent. Okay? So, this is my last example. Thank you for listening and staying, and I hope you learned, or you were able to practice on the lecture using my examples. So again, thank you and goodbye.